I'm going to do something a little different for this assignment. Usually, I have 20, 25 students in a class. I give you an assignment, you upload it to Dropbox, and I grade it, and I give you individual feedback for the questions, whether they're correct or not. And what I'm thinking about doing here is something that I do for my Linux assignment, which is essentially, I'm going to walk through and show you how I do the assignment. And I'm doing that for a couple of reasons. One is that this will essentially provide you feedback on how well you did, so you can look and compare what you did to what my responses were, so you can tell if they're correct or not, and you'll understand your grade better. And the second is it will show you my problem-solving process, and actually if you're lacking in some knowledge area within the assignment on how to run a command or understand a principle, so it'll reinforce what you've already learned, or it will show you where you're deficient on your assignment. So let's see how this works out. So to make it even more interesting is I'm going to use 3 versions of Linux. Some of you say, or I've heard some students say, I don't know how to use that version of Linux. They're all the same. There's 97% of the utilities and the configuration files and all the associated things involved with Linux are the same. So I'm not going to give you something that works on one system and not another. The only instance where there is an issue is when something changes in the kernel. For example, security permissions, the way the kernel handles security, and I found out that does happen. But for this assignment, there was no issue with that. And so what I've got here is a Mint 12. We have an unbranded version of Red Hat called CentOS, which is quite lovely. And we even have server. Yes, we've got server. There's no running GUI. So we're going to do a little bit of the assignment with each one. So the first thing I want to do is I'm going to drop over to Mint, and I'm going to open up a Firefox browser, and I'm going to go out and I'm going to get the assignment. And for those of you who know how to do this, I mean, there's actually a reason behind my madness here, as you'll see, because what I'll show you is how you can share the file among all the different VMs that you have. And so let's go out to 4861. And we'll drop down to the assignment. Here we go. So we have the assignment, and let's go back to our terminal. Let's go to downloads. So we've got, we got a lot of stuff. ls zip. Okay, so I'm going to first make a directory called evidence. Hopefully I don't have one there. And I'm going to move that 4861 to evidence. Spell the name properly in order for the file to work, the command to work. Okay, so we've got 2 different files. We have the CET4861 NTFS Fall 2012, that's the PDF, and we have our DD. Okay, so I've opened the Word document on my host system, and so let's look at some of the questions that we are supposed to answer. Let's make this a little bigger. Okay, you're only to use sleuthkit, and it says down here also you can use MD5 sum. It should say that, but I mentioned that somewhere. To answer the questions, so let's go to the first question. Actually, the deliverables show the command line you use. You can take a screen capture, but crop it. That's all I want to see, and the output of the command. Okay, what is the images file system? Okay, so how are we going to do this? First of all, I'm not sure if I've got sleuthkit on here, so let's type fs stat and it doesn't look like, no, we don't have that on there. So how do we do this? Well, we learned from my Linux course that you install sleuthkit with sudo aptitude install sleuthkit. Then I'm going to pause this because this will take a few seconds, but that's the way you install it. I showed that in the video. Notice that Y is the default. Hit yes. I'm going to pause now. Okay, and we have sleuthkit installed. Okay, so as I explained in the sleuthkit video, that it is a compendium of utilities that are used with file systems or images, and you can use them to analyze for the file systems and file system information, file information, directory information, recover files, and so on. And so actually, this assignment was very easy because I showed you how to do a lot of different things with sleuthkit. All you had to do was to tease out or identify what I discussed in the sleuthkit video and apply it to these questions. So it's very easy to do. So what is the images file system? And so if we go back to the sleuthkit videos and we, FS file system stat, this is the first command that you're going to run that will answer, provide you the information that will answer quite a few of the first questions. And so fsstat displays general details of a file system, and we're going to be running this on an image. Now you probably have guessed that the image file system type is NTFS. You know, that's what we're discussing, and it was actually named NTFS, so you should have been able to guess that. So fsstat, and we can type T and NTFS right here. But just for grins, if we look at, let's see, what is the name of this file? If we look at using a binary viewer hex editor, is it one of the first few bytes in here indicates what type of file system it is. So when you use these sleuthkit commands, if it can identify from the master boot record, as you recall, that's the first 512 bytes of an image. If it can identify what type of file system it is, you don't need that -T for type. Type Q to quit. And so let's type fsstat and NTFS fsstat on the image. We type less, pipe that to less, and here we go. Okay, the file system type, NTFS, the volume serial number, the volume name or volume label, and the version of the operating system that was used to create the file system. And so if we look over here, we see what is the images file system. It's an NTFS. We don't have the MD5 yet. It's not included in there, but we'll need to run MD5 sum on that. What is the volume label of the image? We see that that is 4861-NTFS. What OS created the file system? That's Windows XP. What is the cluster size for the file system? What is a cluster? And a cluster is the smallest allocatable file space for a file, and multiple sectors make up a cluster. A sector is a hardware unit of 512 bytes. And so if we look over here, we see that the cluster size is 4096. The sector size is 512. That really doesn't change, but the cluster size can change depending upon the size of the hard drive, as I discussed in the NTFS video. And so we see that the cluster size is 4096. How many sectors makes up a cluster? That's not a question here, but it's easy to see that it's going to be 8, right? Number 6. Wow, we're already on number 6. Oh, let's do the MD5 sum. Let's do that. Okay. So, but we can scroll down here and see the information on the, if it starts with a $sign, what is it? It is a systems file. And that was gone over very thoroughly in the NTFS video. But if we type MD5 sum on NTFS 2012, there is your MD5 sum. How many non-system files exist on the file system, not counting alternate data streams? Okay, now we have to use a new utility. FLS for file ls, list file and directory names in a disk image. Once again, you notice over here that we've got the here it's a -F for file system type, but we already know that SleuthKit should be able to partition that. And if we move down, what other switches might we have to use? The -R for recursively display directories, because there might be directories on here. And this actually gives you some examples down here. Examples are already good, are always good. And I gave you plenty of examples in the SleuthKit video. However, usually go to the bottom and there are some examples in the man pages. Notice also in here you see here's an ffind and an icat. We're going to be using one of those for this assignment. So FLS-R NTFS. Let's pipe that to less. There we go. So we see up here we have regular files. We also have directories and we have special systems files and so on. But some of these things should look familiar to you based upon the original SleuthKit video that I showed. And so this is asking how many non-system files. So we need to take away the ones that have the $sign, and we can go through here. Here's one called notes. Well, that's really not a file. I know I've said that everything is a file in Linux, but when we're distinguishing between directories and files, you know, a directory in a technical sense is a file, but for this case we'll just go with regular files. So we got backo.txt, colon zone identifier. We know that's an alternate data stream. Is it the standard default data stream? Is that for a file will be held in the attribute $capital data. And so although this would be the default data stream, here it also has an alternate data stream named zone.identifier. But that's really only one file. So 1, 2, 3, 4, 5. It looks like spoiler.txt has been removed, deleted. Then we have a directory called photos. Then we have another file with master file table entry 34-128-4. It should say holy crap. I cannot believe a dog can fly, but there you go. Now I have seen everything. Boy, this is a really long file name. .jpeg. Why did I throw that in there? Because we're used to seeing these things like Windows N.txt, because a lot of us come from the old DOS age when we just name things 8 plus 3 as a name. But in essence, we are allowed up to 256 characters on everything starting from the VFAT to NTFS to all other modern file systems, and that's why I threw that in there, just to impress upon you the fact that it can be done. Now I've lost track of how many we have in here. Anyway, let's just keep going. Here's James.jpg is a file. Kion is a file. Silverstides is a file. Spiegel is a file. Incense.jpg is a file that looks like it's deleted. And then we have a directory orphan files. And then we have these other orphan files down here. And so you notice that those have actually been deleted. That's what this asterisk means. List some systems files that have alternate data streams. Let's go back up to top. Okay, we've got badclus, and we have, which obviously that's going to be the default data stream, and it has bad. And note object ID 1, 2, 3. Reparse. Secure has an SDS, SDH, and SII. And so those should be the only system files with alternate data streams. Describes what an ADS named zone identifier is and how it is useful. Let's just let's recover one of those. Okay, the first thing we need to do is to write down the master file table entry for, let's do for IIS.txt, so it would be 36-128-4. And so how are we going to recover that? Let's get out of this. man, ICAT. Output the contents of a file based on its inode number. Now, that's in general, SleuthKit was created for Linux. However, now it can interpret NTFS file systems. So even though it refers to an inode number, we're really talking about a master file table entry number here. And so what we need to do is we need to give it the ICAT. We don't need the file system type, but we do need the image and the inode number as arguments. And so let's do ICAT and NTFS and 36.128-4, and we're just going to pipe this to less rather than put it out to a file. Zone transfer, zone ID equals 3, and what I wanted you to do is to take that zone dot identifier and to Google for it, so I'm assuming all of you got that correct. And you can do that for all the files with the zone identifier information, and you'll probably know what happened there is I downloaded all of those from the internet. Which non-system files have data streams that are resident? What are the contents of those files? So how are we going to figure that out? First of all, what does it mean to say that data is resident? Well, with the old FAT file systems and the VFAT, the root directory entry for a file would contain metadata information. However, with the master file table, rather than being 32 bytes long like the root directory entries for each file, the master file table entries are 1K, 1024 bytes, so it can hold more information. So for very small files, if the files can fit within the standard data attribute, they are stored within the master file table if they're not too long. But how do we figure that out? Well, this one actually takes a little longer to run because you're going to need to run this on all the non-system files. But the first thing we can do is to go back and run FLS, and if we output this to a file, we could have done that, and then could have referred to this. And so let's go up here and let's take a couple of different examples just to see, because I'm not going to go through all these. Let's look at really.txt 39-128-1, and then we'll look for James.jpg, and that's 32-128-4. Okay, so we have a couple of files in there. And so what we can do is, notice that we have all these commands called stat. So what if we just ran stat on NTFS 2012.dd, as you saw in your introductory forensics course, and you should have had it in Linux, is that stat just gives us metadata information about the file. And so this is the file, the image NTFS.dd, the size, the number of blocks, the access modified and last change time, who owns it, the access controls on it, and the group ID associated with it. If you want to find more specific information about a file, you can run something called istat. And you need to provide the name of the image. And let's look at 39-128-1. We'll pipe that to less and see what it tells us. Okay, it's entry number 39. Log file sequence number, which means it may have something in the log file regarding that, the number of links. That should be hard links. Standard information about the file. Notice it's going to have more date and time stamps. It's got it created. We do know that the MAC times for Linux are interpreted somewhat differently than they are for the Windows-based file systems. There's a created time for the file created. File modified, it's interpreted the same. Access is interpreted the same, but the master file table modified is something that's different that we don't find in Linux. But it shows you that really everything was created all at one time. So go down to the file name attribute values, and we'll see something interested in here. Keep on going down. If we go to the bottom, the attributes, this is the file name, attributes, value. But we go to the attributes, and notice that down here it says for the attribute standard information, the file name, the data, the name not applicable or not available because it's not an alternate data stream, but it's the standard default data stream, and the size is 22, and it's resident. And the reason it's resident is because it can be, because it is it small enough. So how do we see? Okay, let's just stop there because I think later on I show you how to recover that. So let's go to the next one, which was James. This was 32-128 128-1-4 less, and let's see what this is. So you're going to have to do this for all the non-systems files, but it's fairly easy to do. That's good because repetition is important. So we can go to the bottom here. Now notice that this has a lot more information for a couple of reasons. Notice first, if we go down to the default attribute data, name, again, not available, or not applicable. It's non-resident. Why is it non-resident? Look at the size, 45 to 12 bytes. What is this thing right here? 653, 654, 655, all the way down to 664. This is the run list. This tells you where and how many clusters that this file takes up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 clusters are required to hold this file. And that, notice that it's non-resident, which means that this information, that these clusters are not within the master file table. Also notice that it's got another data, but it's a named data stream, zone.identifier, which is also non-resident. What is the file size for really.txt in bytes? I skipped something. Okay, so the two of those, if you went through all these, really.txt and spoiler.txt were the only two that had data that was resident. So they were small files, and I created those on purpose so that you could see what they look like. Okay, what is the run list for the photo of the scuba diver and the US flag? Okay, so what I really want you to do is to be proactive, because I don't remember if there was anything in here that mentioned anything about a flag. So what it's required you to do is to go in and recover these files. Oh, that's so hard. Look how many files there are. 1, 2, 3, 4, 5, 6, 7, 8, 9. If that takes you more than 10 minutes, you're working slowly. So let's look at Spiegel, which is what that was. 29-128-4. Let's get out of there. Okay, how do I recover it? Remember ICAT. Output the contents of a file based on its inode number. So we're going to run ICAT. We're going to give it the name of the image, and we're going to give it the master file table entry number. And this is it, right? Oops, I don't think so. 29.128-4. Okay, if we just output this, what's it going to output? Well, it looked like it was a JPEG file, right? Okay, we're at a terminal that represents ASCII characters on the screen. A JPEG is going to have binary characters in there, or it's going to have characters outside the normal scope of the ASCII character set, which means it's going to give you a bunch of gobbledygook that you can't see. So what we need to do is we need to output this to a file so we can view it. Doesn't that make sense? Here we go. Okay, now how do we view it? Come on, people. Let's go back up to Applications. Let's go to Graphics. Let's go to GThumb Image Viewer. That should work. Let's go to evidence. And there's a picture. There's a picture of a scuba diver with the U.S. flag. So, wow, what was the question? What is the run list? Okay, so we know that's the correct file, right? Okay, what is the run list? Okay, if we know we got the correct file. Whoops. Now, you see what I'm trying to do here? I know some of you don't see the advantage in being forced to go through here and look for things which you feel are almost random. Let me tell you something. That's what forensics is that there's certain procedures you can follow to get the information. However, sometimes you just have to walk outside and look around the ground and see what's there, but you have to know how to interpret the information when you find it, and also know kind of where to look. And so if I just gave you the procedures and said, do this, do that, do this, you wouldn't learn that that's part of the process sometimes. Is it's not straightforward, and you have to search for this information. You have to look at everything. So let's run ISTAT. What's the run list for this? 609, 610, 611, all the way down to 620. And so that's the run list for the photo of the scuba diver. How many sectors does Kion.jpg occupy? That's kind of like the same question as we saw before. Okay, what was Kion? What was that? Let's go back to FLS. Run that. Kion. Let's scroll up here. Where was that? Right here. Okay, we want the -4. 33-128-4. And then we can run ISTAT NTFS 33-128-4. And what is the file size? No, how many sectors does Kion.jpg occupy? Is this a trick question? No, it's not, because I've already told you what the difference is between sectors and clusters. So these are the clusters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12 clusters. 12 clusters. How many sectors are in a cluster? 8, 96. Okay, how large could James.jpg be before it have an additional cluster allocated to it? Okay, this is some simple math. How large would James.jpg be? Okay, so I didn't write down which of these was, so FLS, gotta go back and find for James.jpg is 32.128-4. Okay, and so we need to run ISTAT on that. 32-128-4. Okay, so the file size, write this down, 45,212, and the number of clusters is comprising that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 clusters. Okay, so the file size is 45,212. Pull back calculator up here. More than likely, just from looking at that, that file didn't take up all of the clusters that were allocated to it. That is, there's some slack space at the end of that file. So how many bytes does 12 clusters hold? Well, 12 times 4096 equals 49,152. How big was the file? Minus 45,212. Should be right. And so the slack space was this. That's the amount of slack space. That is, you could have actually fit more file in there. It's just not necessary. And so, going back to our original question, is how large could James.jpg be before it would have to have an additional cluster allocated to it? Well, the answer would be 12 times 4096 equals this. So anything larger than that, it would have to have an additional cluster. When was Spiegel 2556-S last accessed? Well, looks like we're going to have to, I know I keep running back and doing this, but I'm doing this on the fly. FLS, what was Spiegel 29.128.4, 29.128.4. So let's run ISTAT on that, 29-128-4. Whoops. See, I'm working too fast. NTFS. Here we go. Last access, Tuesday, August 28, 12, 27, 42, 212, 2012. Okay, what information is visible in the file system journal log file? And I told you what I did here, and I'll just show you. What I did was I created, I don't know how many of these, 3 or 4. And so I tried to do some interesting things. I tried to make some files resident, which worked out okay. Previously, I've created some of these images where there were an entire file was in the log file, and you could actually read the contents. I gave up after 3 or 4 attempts because it just wasn't working out. I need to get this out to you. So here's what I did. So the first thing we need to do is we need to get the master file table entry number for the log file 2-128-1. Let's output that. So ICAT NTFS 2-128-1 and log file. Here we go. And then the next thing I did was I piped that to strings, and you could have done this in one fell swoop here, but I'm not. Log file dot strings, and what strings does, as we discovered in previous classes, is that it extracts all the human readable ASCII characters of a certain length from a file. And now let's look at log file dot strings. There we go. RSTR, RSTR, RCRD. So those are human readable strings. It's too bad that there weren't any actual ASCII characters outside of those in the log file, but that's why I made it very explicit what you should do. So now we can open NTFS 2012.dd, and let's search for RSTR. There we go. Okay, so RSTR, notice that we have these characters N.T.F.S. What is that? That's the file system type. Where do we find that information? Well, we definitely know that it's one of the first few bytes in the entire image, right? But notice that it's not an ASCII. If it were an ASCII, it would look like this. This means that it's represented in Unicode. Okay, so we can scroll down, see if there's anything else in that log file entry. Doesn't look like it. Doesn't look like it. So let's hit N to search for the next one. Looks like a duplicate of the previous one. Okay, let's type GG, go back up to the top. Now let's search for RCRD. And, well, there's one. And I have no idea what that is. Let's keep going down. And I don't recognize anything in here. It's actually character sets being represented. And so I'm going to be very liberal in my grading of this. I just wanted you to see that sometimes you need to dig in and find stuff like this. It's not always easy. Let's hit the N to search for the next occurrence of RCRD, and let's scroll down with a little J, and you see here once again 4.8.6.1. So we have what? What is this? This is the volume name or volume label in Unicode. If you want to scroll down a page at a time, hit the space bar. But that's all I wanted you to find. It's another one. Same thing. Okay, so I just want you to see how sometimes you have to dig in. You have to use your smarts and what few tools you have to find the information that you're seeking. Okay, a few non-systems files had alternate data streams. Ignore those labeled zone identifier. Recover those alternate data streams, read through them, not all, but get a gist. What are the topics being discussed? Okay, so we need to go back up. Control R, FLS, LS. Okay, zone identifiers, a bunch of them. And we have a couple of alternate data streams here. We have IIS.text in _orange.text. Let's recover that one. 36-128-6. And Windows N.text, the green book. 38-128-6. Okay, so hey, let's recover those. Oh, by the way, that spoiler.txt, how did you recover that? That's a deleted file, right? So is incense.jpg, right? How do you recover those? Well, you recover those with iCat. Let's recover spoiler.txt while we're at it. I know that wasn't a question. Actually, you did have to recover that to get that answer for one of the questions. Where's spoiler.txt? There it is, 40-128-1. ICAT NTS 40-128-1. Clark Kent is Superman, and I hope you've seen the movie, so that was a spoiler. Okay, let's recover those two files. So the first one is ICAT 36-128-6. Let's put in the name of the image, and we'll call that the orange book.txt. And scroll back up, and 38-128-6, and let's call that the green book. Wonder if you've heard of any of these before. Oh, watch my typing. Here we go. Okay, let's look at the orange book. Whoa, there we go. A Guide to Understanding Discretionary Access Control and Trusted Systems, National Computer Security Center. Fort George Meade, it's really Fort Meade, Maryland. So, Fort Meade is the NSA. Okay, so you know what that is, and you can Google for, it might say in here who wrote this. You know, let's look at the green book. Department of Defense Password Management Guideline. Look at this. Look how long this file is. Holy moly. This is an alternate data stream. This is the alternate data stream. Well, let's go back in here and take a look at this. Let's go back and look at, that was the green book. How large was the actual file? Windows N.text. 38-128-3. ISTAT. 30. NTFS 38.128.3. Okay, so this had two named alternate data streams and the standard default data stream. The file size, look, the alternate data stream was larger than the actual size of the file, of the standard data stream rather. How large could this be? As large as you want. Okay, how much more do we have to go? What is a log file? It holds transactions. What kind of information can you find there? Information's on transactions, files, directories, and so on. Answer the difference between resident and non-resident data. How many deleted files exist on the image, if any? If any were deleted, what were their names? Recover them and provide a brief description. Okay, so flip back up here. How many files were deleted? The orphan files, don't worry about those. Instance.jpg was deleted. I believe there's one more. Spoiler.txt. Okay, so you saw what spoiler.txt is. Instance.jpg, you would use the same command using icat and recover that, and it's just a photograph of some instance that I took. And you get the file size from istat, and you get the MD5 from running MD5 sum. The last question is why. Why? That's a good question. Okay, so I hope you found this this walkthrough educational, and you see, the stuff, once you start doing it, it's not that difficult. I gave you all the commands that needed to run. There really wasn't anything in there that I hadn't given you. It was just you selecting the commands and realizing what commands give you what type of result and being able to explain it. And those are important skills that you need to understand when you're doing forensics.